All right, it's 2:30, so let's get started. Title of the talk is SIMD Programming in JavaScript. My name is Peter Jensen. I work for Intel. And yes, Intel does software. Especially recently, we have gotten behind HTML5 technologies in a big way. And one of these ways is pathfinding for new features we can add to JavaScript to utilize the amazing power that we have in modern CPUs. And I'm going to start you off with a demo. It's a simple Mandelbrot demo that's utilizing the technology I'm going to talk about and give you more detailed information about. But just to see what's possible using this technology, I'm going to, let's see. I wrote this demo in, it's a simple Mandelbrot animation using regular plain old JavaScript, and then I wrote a version using these SIMD extensions that you're going to hear about. And without using SIMD extensions with regular old JavaScript, you're going to get roughly between 9 and 15 frames per second here. Now, if we turn the SIMD feature on, you'll see it speed up to between 40 and probably drops down to like 25 or so. The frame rate is determined by how much time it takes to compute each frame, and how much time to compute each frame is determined on how much black you have in the image. So the more black, the longer it takes to compute it, ironically. So let's stop this guy. SIMD is an abbreviation for single instruction, multiple data. It's basically a form of data parallelism at the instruction level. And data parallelism in the form of vector programming is not something new. It was being used back in the 70s by CDC computers and Cray computers when the mainframes were ruling the world. When microprocessors came on the stage, these SIMD instructions were added probably in the mid to late 90s. Started with something called MMX instructions, but what they do is they operate on initially 4 elements at a time. So instead of having to do, say, 4 additions in 4 individual instructions, you can do all 4 of them in one instruction and theoretically get a speed up of 4. Intel's hardware engineers are busy adding more and more of these SIMD instructions every year, and they make the vectors wider and wider. And the widest one we have right now supports up to 16 32-bit float elements in the latest architectures. So a brief history. This project started last year. It's a collaboration between Mozilla, Google, and Intel. The spec, the API that you're going to program against, was initially proposed by John McCutcheon. It has later, through this collaboration, been enhanced and extended. And we actually have prototypes of this working in Chromium and Firefox nightly, and Intel's own web runtime called Crosswalk, which I'm going to talk about later. So why is this important to JavaScript? Well, JavaScript is one of the most popular languages in the world today. I don't know if you can see this graph, but this is a tweet by Joe McCann. He counted up the repos in GitHub and categorized them by language. And guess what? The bar you see on the right-hand side there, that's almost 2x. The one next to it is JavaScript. So by far the most GitHub repositories is JavaScript-based, which is a good indication that JavaScript is taking off, which is not surprising because with the leaps and bounds in performance that we have gotten over the past 5-6 years, starting with SpiderMonkey and TraceMonkey in Mozilla and V8 and Chrome, now with the performance we have from JavaScript execution, you're able to run full-fledged games from both Epic and Unity that have been compiled down to JavaScript from their original implementation language, which was C++, using a tool from Mozilla called Scripton. And it compiles down to a subset of JavaScript called ASM.js, which all browsers are able to execute very efficiently because it can guarantee type safety and eliminate a lot of the type checks that you would otherwise need to do. Furthermore, JavaScript is used to write mobile apps now, standalone mobile apps that are wrapped in web views and can be installed from app stores and so forth using hybrid technologies. You have operating systems that are entirely based on developers writing their application using HTML5 technologies. So the whole application, there's no native code at all in apps for Chrome OS and Firefox OS and Tizen. But these operating systems obviously aren't the most popular operating systems in the world. Windows and Mac OS probably still are. And for that, there's like tools like Node WebKit where you can still access features of the file system and the various other things that native desktop applications will need to do, and at the same time get access to the 20, 40,000 whatever node modules you have in NPM these days. And I mean, full features web apps that run in the browser like Google Docs and Maps and are based on and completely implemented in JavaScript. So there's no question that JavaScript is a popular language, and tons of code and logic is being written using JavaScript. Even on the server side, which has typically been the reign of PHP and Ruby, it's starting to make inroads via this Node.js tool. So why is this a problem? Because newer CPUs, more than half of the instructions in even older CPUs deals with operating on SIMD data. And if there's no way to use these instructions in one of the most popular languages you have, JavaScript, there's a disconnect. I mean, we got all these transistors sitting there in the CPU ready to do work for you, but there's no way that developers that are writing their application in JavaScript can use these, which obviously is a huge disconnect. This is what this SIMD technology in JavaScript is supposed to address. So when people do SIMD programming, they probably do it in C and C++. Granted, there are dedicated languages that will allow you to do apps that deals with massive amount of data and operations that needs to operate on these, like MATLAB, and there's extensions to the C language. There's Intel's array notation, for example, that's supposed to have a nice abstract way of expressing these vector operations. But all these methods comes with an abstraction penalty. And sometimes that abstraction penalty is exceeding what the gain is that you're getting. So what you typically see in C and C++ programs for people that really care about performance is that they use something called intrinsics, which is basically a slight abstraction from the pure instructions themselves. So this little 6-line piece of code, I don't know, I hope you can see it. It's hard to make it any smaller. Just averages up the sum in a float array, or a float array pointed to by source there of length lang. And the scalar version is up on top. And if you want to do a vectorized version that utilizes the power of the SIMD instructions that's available in modern CPUs, you got to write this ugly piece of crud you see down below here. So these 6 lines of readable C code turned into 20-some lines of unreadable use of intrinsics here. I mean, if you look at this from a software engineering point of view, they would say, why would anybody do this? But the reason is that they want to extract the performance that's available in modern CPUs. So just to see what corresponds to what here, to initialize the float variable that holds the sum that you're adding up over this array, you will have to call, in the case for Intel, an intrinsic called set0_ps. Okay, that's not entirely obvious that it initializes a 128-bit word to hold 4 32-bit zero floats. but that's what it does. And the naming of these intrinsics, at least in the case of Intel, is largely legacy-based. I think was multimedia initially. Underscore PS there is packed single precision. And in the case of ARM, it's not much better to initialize it to 0. It's called v.q underscore n underscore f32. I mean, if you don't have a manual next to you, this code is pretty hard to read. And it goes on. I mean, adding up, instead of adding just one in the scalar case, you can add up 4 elements at a time using this add underscore ps in the case of Intel and v add q underscore f32 in the case of ARM. Not exactly beautiful code, and not exactly easy readable code. Then when it comes down to summing up those 4 buckets that you have partial sums in and dividing them by the total length to get the average. In the case of Intel, a good way to do that is to store out the 128-bit 4 times 32-bit floats into memory, and then reading each of these 4 buckets and adding them up and dividing them by the length to get the average. In the case of ARM, they actually have intrinsics to properly extract a lane from each of these, a lane from the sum that holds up the 4 buckets value there. So, and then if you have an architecture that doesn't support SIMD, you'll go down to the else part of the if-def macro here to just call the scalar version, just so that the code always works. Now, if you want to do this in JavaScript with these SIMD APIs that we have proposed, you would basically be able to express your logic in the same way as you did with the scalar version from before, in 6 easy readable lines of code here. They're a bit verbose. I mean, to initialize the serial, say simd.float32x4, which is the object hanging off the SIMD object that denotes all the operations that you do on float32x4s, .splat to initialize each lane to 0. And to be able to access the elements in the input array as 4 times 32-bit floats, you would overlay it with another float32x4 array where the element type is actually these float32x4s. And then you would do the add using the .add operator. And the .getAdd here is a placeholder because we couldn't override the square bracket index operator on the on that new type of typed array that you have, float32x4 array. So for now, it's called getAdd, just to get to that element. But essentially, it will load up 128-bit, all 4 times the 32-bit floats there in one chunk. And then to extract the lanes, you just do .x, .y, .z, .w to get the 4 elements in the And what we've been able to get with the prototypes that we have implemented is performance that's totally equivalent to C and C++, because we have this tight mapping between the primitives that we have defined and the actual instructions that are available in modern CPUs. That's almost a one-to-one mapping, so it's relatively easy for the JavaScript virtual machines to map these to actual instructions that do as you would expect them to do. So the benefit, of course, is we have shared code that runs equally well on both ARM and x86 at the moment. And it runs on all architectures, all operating systems, and all browsers. And the little dagger symbol there, of course, is the caveat is that a SIMD browser must be available on the architecture and the operating system we're talking about. So when I was thinking what I could use as a really good motivating example for this talk a couple of months ago, I was playing around with a game that probably a lot of you have played as well. It involves a little bird that goes up and down. I gave him sunglasses to avoid copyright issues with the image. But anyways, yeah, it's a physics. It's a one-directional computation of the position. And it has a little collision detection down at the bottom where it's got to reverse its velocity when it reaches the bottom. So I wrote up a little JavaScript example here to see if there was any performance issues, but there wasn't. I mean, you do the performance profiling in Chrome, for example, and you'll see most of the time the CPU is sitting idle there at 97% of the time, and the time it takes to find out where to place this bird for the next frame is pretty minimal. And the math behind computing where the bird should go for the next frame is based on its velocity and where it was in the previous frame. And if you remember high school math, this is the formula it takes. So just to compute these two values, and you got, if you want 30 frames per second, you got 33 milliseconds to do it. It should be pretty doable in pretty much any JavaScript VM that we have today. So what can you do to make it take more CPU time? So this would be a motivating example. Well, you can add more birds, but even if you do that, you're probably going to overflow the screen with just massive amounts of birds because you can do this many, many times. Now, if the so the JavaScript code basically is just this little loop here, and assuming you had more birds, the number of actual birds is held in this variable called actual birds, and the position and the velocity of all the birds are held in these arrays, parse array and veloc array. And the formula you saw on the previous page is basically what this JavaScript code computes. And the if statement inside the loop there is what reverses velocity when it reaches the bottom. The collision detection. And that's an interesting part of the loop because loops that have control flow in them where you don't do the exact same operation on the data for each element in the vector is a little challenging when it comes to vector programming, as you'll see later. Now, to further make this compute intensive, I thought, okay, so what if the acceleration is not constant? What if you're living on a planet where the acceleration jumps up and down every microsecond or whatever? The formulas become a little more compute intensive because, say, within each frame, the acceleration changes n times. These are the formulas that you need to use. You need to sum up this randomness in the acceleration. And depending on how many different values you have in that step function, this can be more or less compute intensive. So I basically adjusted this n parameter to make it enough compute intensive to be a compelling example. And let's see. The SIMD version of the code that does this computation have an inner loop besides the loop that deals with the birds, which is the outer loop. And the way that the collision detection is dealt with, so first of all, you'll see that the iteration count of the outer loop is divided by 4 here, shifted 2, so that you're computing the position of 4 birds at a time. And the collision detection down here, since you don't need to reverse velocity of the birds that haven't reached the bottom yet, is using this select operator, which so it does compute the negative velocity of all 4 birds, but it's only updating the new velocity if the current velocity has exceeded the max position. So this is a way to selectively choose either the value from new val true x or the value from new val x4 there. Now, the example becomes a little more interesting. So you'll notice that right now it's running using regular JavaScript, not using this algorithm you saw on the previous page. And for some reason, if the zoom factor is not 100%, the rendering takes a bit longer, so you can't have as many birds in this animation here. But the way that the animation works is that it'll keep adding birds until the frame rate is around 30. And right now it seems to have stabilized around 133. Now if you switch to using this SIMD implementation of the position computation in frames, we should see that it's able to deal with many more birds and still maintain the same frame rate. So roughly a 3x increase here. The blue ones are the ones that were added once I switched to the SIMD implementation of the position computation. And if you turn it off, it should be a little stuttery because it can't maintain the 30 frames per second, so it needs to drop off the blue ones again until it gets down to about 30, and then it stabilizes. Now the why are we not getting 4x speed up here? Because all the compute-intensive stuff, you're essentially executing 4 times fewer iterations in that outer loop. Now, if we do a little performance profiling, let's see if this works. Recording a little time here. You'll see for the non-SIMD version, about 22.5% here if the time is spent in program. And when you see program in your performance profile, what that typically means is it's doing rendering. The WebKit runtime engine is doing something that's not related to the user's program necessarily. But the update all, which is the function that updates the position of these birds, is taking up 75% of the time. And if you look at the flame chart, which is a pretty useful thing here, you'll see the time between the program and the update all. You see this nice periodic pattern here, and the length of the program and update all added together is about 33 seconds, which is the time between frames. Now if we switch to SIMD on and does a similar thing with the let's just see this. Now you'll see that the percentages are a little bit different. The update all, which is the SIMD version here, is only about 58%, and the program, which is the rendering, is 34%. So this indicates that the WebKit runtime needs to spend more time rendering. So this is the explanation on why you're not getting a perfect 4x speed up, but more like a 3x speed up, because the percentage of time that you're actually executing this update function is less. So, okay, same thing here. So for the Mandelbrot one that I started out showing you, the Mandelbrot computation basically, for each of these pixels, you compute the color by doing this iteration. And if the iteration converges or diverges, if it diverges, it colors it black. Or if it diverges, the color, the number of iteration it takes to diverge is mapped to a color that's then put in that pixel. And for the black ones, those are the ones where it doesn't diverge. Again, if you turn SIMD on here, you'll get a roughly 3 times speed up.
So, is the SIMD extension in JavaScript, is it going to be able to tell you that you're running on a machine that will actually benefit from the speed up versus the virtualization?
We are hashing that out right now. Right now, the way to see if these extensions are available is to see if SIMD, the object SIMD type of, is undefined or not. But whether the features, because we have polyfill for it, which would make it defined, but it's not going to give you speed up, is something that we're discussing, because there might be architectures that are not willing to put in the engineering resources it takes to do a VM that enables this feature.
I mean, I guess what I was getting at is, do you consider it an important use case that an application would only want to opt into trying something, not just because the API is there, but because it's actually going to get a 3 to 4x speed up? If it isn't going to get the speed up, maybe we just don't even use that feature. Is that an important use case?
I think so. So the kernel, in case you're interested, looks like this. Again, 15 lines of JavaScript code, which is not terribly complicated. I mean, the most complicated part is this piece in the center here where it's determining whether to keep counting or not keep counting. So since you need basically 4 iteration counts returned by this function to represent the colors in 4 pixels, and they're not all gonna diverge at the same iteration count, you need to keep 4 separate count values. And the way you do that is basically ending out a mask of 1s for the ones where the this compare up here failed. You'll end it out because the sign mask will be 0 for that lane, and for the ones where the compare succeeded, you'll have 1 in this bit mask, and when you add it into the count, add it to the count, then you only get increments for the ones that needs incrementation. So the API details, right now it's fairly simple. We only support operations on 2 types, float32x4 and int32x4. And we have some constructors. You can initialize each individual lane for both the floats and the ints. You can initialize all lanes to the same value, and you can set them to 0. Then you can access the lanes individually using .x, y, and c, and w. And there's mutators where you can, if you want to keep the existing values, create a new object with just 1 lane changed. And then you would then you have the expected arithmetic operations on them. You can do shuffles, and I'll get back to a good shuffle example here in a bit. You can do logical operations on them and comparisons, shifts, convert between them. And then there's various clamping operations and min-max operations. So shuffling, that's one of the more interesting SIMD operations you can do. Say you want to transpose a matrix, 4x4 matrix, not an uncommon operation in WebGL-based games where you have to feed these projection and view matrices into the WebGL engine. A transpose operation where you would typically need to move the 16 individual elements around to get them in the right position for the transposition. You can do that very efficiently using shuffling. So first you need to extract the 4 rows there into 4 individual float32 x4 values, and you do that using the get@, index operator. Once you have them in 4 individual values here, you need to shuffle them around so that these that were previously rows becomes columns. And first you'll need to, you can't do this in one shuffle operation, unfortunately, because the shuffle operations only take 2 operands. And in order to get to a column from a row, you need elements from all 4 elements. So you need to do it in 2 stages. And first you'll get an intermediate result here in the that extracts basically what you need for the first 2 columns into 2 temporaries. And the way you do that is using the shuffle mix that takes 2 operands, and you specify using a bit mask where the individual elements in that vector should come from. So xy, the first xy's indicate that they come from lane x and lane y, which holds the 0 and 1 there in the top one. And the second pair of xy's indicates that the second 2 element comes from the x and y lane of the second operand. And when you have them that means that you have all the 4 elements that you need for the 2 first columns there. You do another shuffle operation between these 2 intermediate results to actually get to the 2 columns that you need. So these are the 2 columns that you will need to have for the transpose result. So if you combine all these, you do the same for the next 2 columns, by the way. You get this matrix that now looks like this, and then all you need to do is move it back out into where it came from so that you have it effectively being transposed. So right now we have...
Peter, question?
Yes?
On the latest vector instruction from Intel XDK 5.12, where the bit is 16, you can actually do this in 1 operation.
You can. Unfortunately, we still haven't exposed these types in this API yet. So we have prototypes implementation of this. We got one in Firefox nightly, and there's two stages to this implementation. It needs to be implemented in the interpreter part of Firefox, and it needs to be implemented in the JIT part of Firefox. And the JIT that we're currently targeting is both IronMonkey and OdinMonkey. The interpreter part has landed in nightly. The JIT part is not landed, but we have it functional. We can do demos with it. For Chrome, similarly, we have Chrome doesn't have an interpreter, so we only have the JIT implementation that's available in Chrome. We have submitted the patch to Chromium. It's not yet included in nightly. Now, Crosswalk, which is Intel's own open source web runtime. It's based off of the Blink repository from Google. That's originally based off of the WebKit. But there we have it, and there's a beta version available today that you can actually download and play with. And there's demos out in the booth here in the at the conference where you can actually see this in action. I encourage you to stop by the booth, the Intel booth out there. Where do we see this being used? Especially games that uses a lot of vector matrix and stuff like that for doing computations of where things needs to go, and especially feeding in data to WebGL. It typically involves a lot of vector math and matrix math. And the physics parts of these games also could benefit. As you saw, this very simple example I had was able to deal with many more birds at a time and still achieve the same frame rates. We found some cryptography use cases that could be sped up using this API. Obviously, there's image and video processing. We're currently looking at the VP9 codec from Google to try and speed that up. Audio and signal processing that were previously also just the domain of natively compiled languages. Fluid dynamics, finance, computation. In general, compute-intensive stuff that has been able to utilize vector instructions in the past, and for statically compiled languages are areas that JavaScript now can be used for. Thus bridging this gap and disconnect between the hardware and the software that developers want to use scripting languages, and they can now utilize these features in hardware that they previously couldn't. So we have some benchmark results. We extracted kernels from some of these application domains, and as you'll see, that's heavily focused on matrix operations. I think 4 of these kernels are based on matrix operations, and for these we get a good more than 4x speed up. Some of this speed up is more than 4x, and you might ask, why is it more than 4x when you only do you can do 4 times as many operations in the same set of instructions, but so theoretically you shouldn't get more than 4x speed up, but here we're seeing up to like 9x for the inverse operations. And unfortunately, it's a side effect of the scalar version that we're comparing against needs to do all the math operations in the JavaScript number type, which is 64-bit floats. And the SIMD kernels that we're comparing with does all the operations in 32-bit float. So you're comparing a 64-bit float kernel with a 32-bit SIMD kernel, and it's not quite a fair comparison, but we expect similar speedups for if we were to do 64-bit floats in SIMD. Currently that's not possible, so this is what we have. And yeah, as I said, you can use it today. All you need to do is download the Intel XDK. This presentation itself, I actually got running on this tablet I'm going to show you in a minute, and I was using this Crosswalk runtime to build it and create a hybrid HTML5 app that runs on the device very seamlessly in less than 5 minutes. You just go to the Build tab, select the Crosswalk build, and you got to select the beta version because this feature is only available in the beta version when you go to the details page on the Build Service tab. So let me try to do this device demo. Yeah. Hopefully this is going to work. I got this tablet here. I don't know if I hope people can see it. Okay. And as I said, I wrapped up this whole presentation as an HTML5 hybrid application. I'm going to open it up now. Okay, here we go. And let's go to the birds. So here, this is the Samsung Galaxy 3 with the Intel Atom CPU in it, and we have the SIMD features enabled in the runtime, in that crosswalk runtime that's used to build this application. So theoretically, I should be able to hit the SIMD button there to enable this feature. And you'll see, obviously, it's not as performant as my laptop. I can only get about 12 birds flying around there at the same time without SIMD. But let's try to turn SIMD on. And again, you get a good 3x speed up like I did on the desktop. So at least the factor of speed up is about the same. The total number of birds that you're able to keep flying here is not. But so the whole presentation is basically hosted as an HTML5 hybrid app that it took me 5 minutes to create after I had it working on the desktop. So I was pretty happy with that. All you had to do was load up your sources for this Reveal.js presentation in the XDK and hit the build button, and back came an APK that I could download and do an ADB install on the device here, and it worked. Not that I was surprised that it worked, but it So going forward, we need to finish the prototype for Firefox, the JIT part. And then for the, as far as making this part of the JavaScript standard, we were planning on proposing this as being part of ECMAScript 7. There's a July meeting in the TC39 committee in July, hosted by Microsoft, where we're going to make a proposal, and hopefully it'll get on the agenda. ECMAScript 7 is still a few years out. ECMAScript 6 is not even the official standard yet, so it has a long time coming. But again, we need to close this discrepancy between hardware and software that we have right now. Other things we're working on is a short vector math library for having higher order math functions like sine and cosine. Currently, there's no support for these in the way that the SIMD API is defined, but the way that we plan to implement this is using the current low-level API to implement these just like they have done in C and C++. We also envision people will start creating optimized versions of existing libraries, Physics.js, Box2D, GLMatrix, and so forth. Some of the popular ones that are currently used to make web-based gaming. And who knows, maybe higher level abstraction libraries. I mean, there's a lot of clever minds out there that can come up with innovative ways to use this technology that we haven't even thought about. I'm sure of it. The references here, there's a strawman proposal out for the ECMAScript TC39 committee. There's a polyfill, so you can actually check the functionality of your program if you use this API without having a browser that natively supports it. The performance is not going to be the greatest, but it will work. There's a paper published, and it was presented at the workshop on programming models for SIMD and vector processing in Florida earlier this year. There's a blog post by Axel Rausmeyer that talks about this and explains further. Mohammed Hagigat from Intel has written a blog post, and there's a white paper by Ivan Hibahat that's talking about more details in case you're interested. So as I said, it's a collaboration between both Intel, Google, and Mozilla. The guy from Google that's primarily involved is John McCutcheon. Mozilla, we got Nico Matsakis, Dan Goman, Luke Wagner, Elon Sakai. The latter two are the people behind Emscripten and Odin Monkey, so the other way around, OdenMonkey and mscripten. And at Intel, we got Mohammed, Ivan, Haitao, Ningxin, Wei Lianghin, and Heidi Pan. So lots of people have been involved with this. It's very exciting technology. So with that, I thank you for attending. You can access the presentation on the GitHub site there. Are there any questions? Yes?
Will this also support typed arrays rather than the custom SIMD arrays?
Yes. The intent is that the number of available different typed arrays will be extended to include the float32x4 and the int32x4 array. And when it does, you'll be able to use the regular index operator to actually get to the elements instead of having to use this get@, method or set@, method to assign to it. That's it.
I have a question.
All right.
The SIMD processing, does it happen within a single core, or does it use multiple cores to do that?
It's within a single core. It's called data parallelism. So basically, you're doing these 4 operations in one chunk in the same core. And each core, if you have 4 cores, you can theoretically do 4 of these operations in parallel. Times 4, you can do 16 operations at a time. Oh yeah. If we go back to the Mandelbrot test case or demo. So SIMD is currently on, but I also implemented it such that it can use web workers if there's multiple cores on your CPU, and it'll dispatch the computation of the pixels for a frame to a web worker, and the more you have, the more frames you can compute at the same time. So if you keep adding web workers, this particular laptop has 4 cores, so anything beyond 4 is not going to give you any speed up, but this basically shows that the 2 forms of parallelism, the data parallelism you're getting with SIMD and the task thread-based parallelism you're getting with the web workers, are completely complementary. There's no conflict of interest there. And they're cumulative in their performance boost that they add to the, at least this particular example here. Anybody else? Yep.
What happens if the types of the operands don't match? Do you have
You'll get a JavaScript type error. All right. Thank you.